No tech fintech startup in their right mind in a post large language model world would pursue funding without using AI in their product in some way, or even just throwing AI in their company name. Yet when we go to interview at these shops like Citadel, Jane Street, 2 Sigma, the technical questions don't place priority on machine learning and artificial intelligence. Sure, you may get a question about an optimization scheme or a model here and there, but typically the priority is on fundamental probability and statistics. Why is this the case? Well, in this video, what I want to do is I want to talk about what AI actually learns and make a connection to these foundational topics in probability and statistics. To accomplish this, we're going to look at a couple of simple examples, and then we're going to make the extension to the real world, where we're going to talk about the stock market and facial recognition as two separate classes of problems. Now, as always, this Jupyter Notebook will be available in the description below. I will also post it to the Quant Guild library on GitHub, where you can find all of my Jupyter Notebooks and associated YouTube videos. At the top of this Jupyter Notebook, you will notice some of my related videos applying probability statistics and, of course, artificial intelligence to a variety of topics in finance, which will all be particularly relevant for this video. Moreover, if you are interested in quantitative finance but you do not know where to start, check out quantguild.com. Maybe you have a background in business, economics, or even computer science, and you want to learn the necessary skills but aren't too sure where to look. Then Quant Guild is for you. It has an adaptive practice engine so that you can get up to speed on all of the topics in math, probability, and of course finance, guided lessons, applied trading games, and even live classes with myself if you are interested in taking a deep dive into different topics like the pricing of financial derivatives or generating quantitative trading signals. In addition to live courses, Quant Guild members will soon have the opportunity to enroll in live sessions weekly with myself, where I'll do a deep dive into a particular topic, but more on that later. For now, let's dive right in and start talking about what it is AI actually learns, by beginning with random variables and the different outcomes of different types of random variables. First things first, when we're dealing with these types of mathematical objects, that is random variables, we typically denote them using letters, just like from basic algebra. Here I say y is the outcome of a dice roll, x is the average value of a trading signal. And it's tempting to treat these quantities just like we would any other variable from, say, calculus, but they're not just numbers in the classical sense, right? If I said x is equal to 3, then x certainly is just a number, but here x is the average value of a trading signal, and it's a random variable, or we are classifying it as such, and that means that it follows a distribution. So there's no need to get our wires crossed here. Anytime we define a variable as a random variable, what we need to do is we need to treat it as a set of possible outcomes, not just one outcome. The best way to do that is just think of a distribution. So anytime you see a variable that's defined as a random variable, here y and x, just think distribution. And what is a distribution? Well, I have two examples here. One is the average value of our trading signal, and the other is just a dice roll. This is a discrete random variable, and this is a continuous random variable. And these are what we would call the theoretical distributions for x and y. That is, we are certain that the randomness of x and y are governed by this continuous distribution on the right and this discrete distribution on the left. The outcomes themselves all have different likelihoods of occurring. So on the left, if we look at the discrete outcomes, all of these bars are the same height. So each outcome is going to have the same likelihood of occurring. On the right, that's not necessarily the case. The outcomes in the center are going to be more likely than the outcomes in the tails. When it comes to dealing with these random quantities, there are a couple of really important ideas. The first being whether or not you are dealing with something that is actually random or something that we are treating as random. And another is if you are dealing with the empirical distribution or the theoretical distribution. Let's start by looking at an example to tie all of these concepts together. So The empirical distribution is something that I record drawing from the theoretical distribution. So this is the theoretical distribution of dice rolls. If I was to roll 5 dice and record all of the outcomes, then that would be one instance of an empirical distribution. If I did it with 1,000 dice, then I get a different empirical distribution, and so on and so forth. Now, we hope, and in some cases, the empirical distribution will converge to the theoretical distribution. And if this is the case, then we can make informed decisions about the randomness. So I have a very simple example of this here. I roll 5 dice, I record the empirical distribution. Then I roll 1,000, I record the empirical distribution. I roll 10,000, record the empirical distribution. This is certainly converging to the same theoretical distribution that we see up here. And that is because each dice roll is independent. If I roll a dice, then the next dice roll is not influenced by that previous dice roll, and I'm also drawing from the same distribution. I'm not changing the weight of the dice in between rolls. So when we're dealing with randomness, right, we would like for the empirical distribution to converge to this theoretical distribution, because then we can make very informed decisions about the randomness that we are dealing with. Now, in reality, we don't typically have the theoretical distribution. So the dice roll is governed by this distribution, and I'm suggesting that my trading signal is governed by this distribution, but I don't have the theoretical distribution for my trading signal. The best that I can do is collect a whole bunch of data and approximate this theoretical distribution. That is the best that I can do. Now, the big problem with that is no matter how much I continue to sample, there's no guarantee that the data that I am collecting for the empirical distribution is going to converge to the theoretical distribution in the same way that it did for this dice roll example. It's entirely possible that I continue to collect data for this trading signal, and the data that I'm collecting is in fact time variant. So as time marches on, I'm going to be drawing from different shape distributions, and the empirical distribution is never actually going to match this beautiful bell curve. Something to keep in mind, and a very real challenge that we face when we try to develop these models. Another important note is we're typically treating quantities that aren't actually random as random variables. And what I mean by this is when I roll a dice, right, that outcome is not going to impact the next dice roll. But that's not necessarily true for something like a stock's price, right? Maybe there's insider information that once released is going to cause a massive uptick or a massive downtick in price. That's why insider trading is illegal, right? Because that information predates the impact in price. But with something like a dice roll, any information that I give you is not going to impact the outcome. So when we roll a dice, we're dealing with independent draws from the same distribution, where no amount of conditioning on any information is going to change the distribution. But this is not true when we're dealing with a random variable or treating something like a random variable like a trading signal. We're trying to approximate this theoretical distribution, but if I condition on information, that theoretical distribution is certainly going to change. Not just change with information, but change over time. This is why it is a very difficult problem in reality. So very important topics to keep in mind in the reality of approximating a theoretical distribution like a trading signal. Shouldn't we be talking about AI by now? This is a video on what AI actually learns, after all. Well, random variables are integral to the discussion, and that's because whenever we train a neural network, we are treating some sort of set of features and an outcome as typically random variables. Now, whether or not it is truly random or it is just something that is a giant composite of too many factors to consider, that is subject for discussion depending on your context and your problem. But nevertheless, what we're going to do is look at a very simple example, and then we are going to talk about the dynamics of the AI model. So what we're going to do is we're going to train a neural network on dice roll outcomes. And my goal is going to be to produce the best possible guess for a dice roll. Now, a dice roll is random. So what is my neural network actually going to learn? Well, what I'm going to do is I'm going to set up a neural network. I'm going to feed in some quantity, some fixed quantity, a constant, and the neural network is going to transform it and then spit out the output, which is going to be the best guess for the dice roll. So I'm going to do this a very large number of times to train the neural network. So I'm training my neural network here, and it looks like the prediction for the neural network is 3.52. But what is the expected value of a dice roll? Well, it's 3.5 after all, if we just add up all of the numbers on a dice and divide by the total number of numbers, right? That's just the simple average. The neural network is trying to learn that 3.5. It's suggesting that the 3.5 is actually the best guess that we could possibly give for the outcome of a dice roll. And what I'm doing here is I'm comparing the error of our prediction, that is between the actual outcomes and the neural network and the associated expectation. What you'll see here is that, wow, the expectation actually performs better than the neural network. There's a larger error for the neural network than there is for the expectation. In fact, if I was to roll an infinite number of dice, there's nothing that is going to beat that expectation. No neural network, no machine learning algorithm in this world, assuming independent draws from a fixed theoretical distribution representing a dice roll, there's nothing that is going to beat that expected value. So all my neural network did there was learn the mean value of a dice roll. I just deployed an AI model to try to predict a dice roll, and all it learned was the average. That's all it learned. In fact, this is all AI will ever learn. Sure, there are different architectures for different types of problems that can learn distributions or different types of encodings, but that's not what we're discussing right now. We're discussing that AI, or a neural network, is a universal function approximator for an expectation. Just like we saw with the dice roll example, right? The dice roll is a random variable. We're trying to predict the outcome, and the best that we can do for that randomness is an expectation. Now, how correct the prediction is going to depend on your problem space. Sometimes you will be able to produce a better prediction. I use that loosely, right? It's really an expectation or an expected level. Sometimes you'll produce a very, very good one, and that's because you have sufficient data to discuss the variability in the outcome that you are looking for. And in other cases, you don't, right? So let's talk about what it means for AI to learn by looking at a very simple example to understand why it's producing this expected level. So if we look at something like height and age, right? Clearly, everybody who is the same age is not the same height, right? If somebody is 30 years old, then there are a lot of different heights that they could be. They could be 6'6", they could be 5'5", right? Here's a very simple example of this, right? So if somebody is 25 years old, right, they could be 68 inches, or maybe they are 72 inches. If I was to give an AI model this data and tell it to predict the absolute best height that it could, what would it do? Well, it would have to split the difference, right? That is the best that it can do because it's trying to minimize the distance between all of the data that we have and the potential outcomes. And in order to do that, it's going to have to split the difference. That's the best that it can do for this particular set of data. Sure, if we include other factors, maybe we include gender, maybe ethnicity, maybe those change the level that we're able to produce and we produce better predictions. That certainly could be the case. But in this case, what we're looking at here is the best that an AI model could do is split the difference. And that's really what I mean when we're saying that we're learning some sort of nonlinear conditional expectation is we are giving it all this data and we're saying, hey, what is the best prediction that we can make? Best prediction, best level that we can produce if we see this data first. And in order to do that, really, we just have to split the difference like this in a large number of dimensions. And in some cases, the data that we have is going to be sufficient to produce an accurate level. And in some cases, it's not. In other words, when we're dealing with randomness, the best we can do is an expectation. When we're dealing with randomness that is a consequence of a lot of different factors, the best we can do is a nonlinear conditional expectation, and that's approximated via a neural network. Let's look at a market-making example. Here we have a bid and an ask that is governed by uniform randomness. And I have this historic data of mid prices. My goal is to come up with a prediction for what the true mid price is to be able to quote a more competitive spread? Well, what I do is I train my neural network on this historic distribution, and I find that the mid price is roughly 3.99. If I compute the actual expectation of the bid and ask to produce the mid price, then I get 4. So once again, this is just an example of a neural network learning the expectation, and in this case, the expectation is just the actual mid price. This is extremely relevant in market making. This is extremely relevant in quantitative finance, because if you've seen any of my videos discussing trading, discussing edge, discussing this idea of accumulating positive expected value from the perspective of a market maker or a market participant, it all revolves around the ability to produce an expected value, a level. And you need to be able to profit from that level, right? So all of this is extremely relevant to the space. If you're able to produce a model that produces a good level, and then you can make decisions around that level that contribute positively to your expected value, then that's the whole point. That's the whole point of the space, right? If you can't produce a good level and the decisions you make impact your expected value in a negative way, then at best you're breaking even or you are losing money. Surely when we're dealing with probabilities, we're not dealing with an expectation. Well, hold your horses. A Bernoulli random variable has an expectation, which is just the probability of success. A Bernoulli random variable is a framework for being able to produce probabilities. It's probabilities for anything. Sure, there are a variety of assumptions that are being made in terms of independence and distribution, but let's disregard those for now when we're dealing with something like a dice roll. Maybe I'm curious about the probability that a dice is going to be even or odd. Well, what can I do here? I can roll 5 dice, 1,000 dice, 10,000 dice, and I can record a 1 every time that I see an even number and 0 every time I see an odd number. And what you'll notice is that distribution, that probability distribution, converges to the theoretical probability distribution. This is the exact same mechanism that we saw up here with the frequency. But in this case, we're dealing with a probability. When we take the average value of all of these outcomes, we are producing a probability as an expectation. So when we're dealing with probabilities, even in a neural network, we are producing an expectation. It's an expected level. It's not a prediction. Again, it's the exact same argument as the neural network being applied to the dice rolls here and the neural network being applied to this mid price here. We are producing an expected level for that probability, and we're saying it's governed by some sort of Bernoulli random variable so that we can produce this quantity. So fundamentally, whether we're dealing with some sort of like quantity, like a random variable, like a dice roll or the mid price, or we're dealing with a probabilistic outcome, some sort of event, even or odd dice, stock price up or down, it's the exact same mechanism. It's an expectation. And all a neural network is going to do is it's going to approximate that expectation. I generate 10,000 dice rolls. I record a 1 or a 0 if it's even or odd. And then I tell this neural network, hey, come up with the best possible prediction that you can. And look, the neural network learns 0.49 and the true probability is 0.5. That is the expectation. It is learning the expectation of the Bernoulli random variable that governs this event that the dice roll is even. All a neural network is doing is approximating some sort of expectation function. More specifically, it is a non-linear conditional expectation. That's all it's doing. There's no prediction. It's producing a level. Our advanced artificial intelligence model here can be boiled down to a simple average. Still think statistics and probability isn't important? Goodness gracious, it's no wonder these shops want us to have a very strong foundation in these topics. What I'd like to do now is extend these ideas to the real world, talk about stock price prediction in the context of artificial intelligence and facial recognition. Whenever you use Face ID on your phone, you are conducting an image recognition problem and you're producing a probability in this capacity that we just talked about as an expectation as a Bernoulli random variable. If the model says that the probability it's you is greater than 50%, then it's going to unlock your phone. If it's less than 50%, then it's going to keep it locked. This is why when you're wearing sunglasses, maybe you have a mask on, maybe you take it at a weird angle, the model may not be confident enough that it's you, and the expected probability level is below that threshold, and it's going to keep your phone locked. Now, all of this is relevant because if I'm saying, hey, this is an expected level, why does it work all the time, right? When you open your phone and you actually look at your Face ID, you don't expect it not to work sometimes, right? You expect it to work all the time, maybe a hiccup here and there for those odd angles, but I thought we were producing an expectation, not a perfect prediction. Now, hold on a second. We actually are producing an expectation, and it turns out it's a conditional expectation, and for a problem like facial recognition, it's a heavily nonlinear conditional expectation, but the problem space itself is stable. What I mean by that is your facial features, you could think of it like this, your facial features aren't changing enough such that when you use Face ID, it's not going to know it's you, right? If you were to grow a beard all of the sudden, then yeah, it's going to produce a different probability. Maybe it needs to learn what you look like with a beard. This is the problem space. And the reason why it's so important to understand this is because that's a very stable problem, even though it's time variant, right? Your face may change over time. It still may know it's you, but eventually it's not gonna. This is exactly what we deal with when we are deploying AI models in the stock market. The big difference between facial recognition and stock price prediction, cross-sectional stock return prediction is really what I'm discussing here, is the problem itself is very time variant. It is very unstable, and it is a very difficult space to just apply AI models to produce a level. So what the heck do I mean by unstable? Well, we know that a dice roll is random. If you've seen any of my other videos, producing an expectation for that random quantity allows us to find edge and generate P&L. So the goal is to find that expectation. Why is finding an expectation in the case of real world finance difficult? Well, there is no convergence guarantee. A company that started in 2000 is definitely not the same company in 2025. We're not drawing from the same theoretical distribution. In the case of a dice roll, the theoretical distribution doesn't change. But in the case of a company or a set of companies, the theoretical distribution is changing all the time. So it's a very difficult problem. It's a very difficult problem space, but all is not lost. There are a lot of applications of AI in the generation of trading signals to predict returns in the cross section. And what I mean by that is it's not necessarily about using AI to predict a level, an expectation for a stock price or stock return. It's about using AI to extract a trading signal and then assessing the viability of that trading signal using classical statistics. We don't necessarily need to use an AI model to map trading signal to return and learn to see if there's a relationship there. We can use AI to generate a trading signal and then just use classical statistics to assess the efficacy of that trading signal and then determine whether or not there's any edge and whether or not we can establish portfolios based on it. In any case, we're dealing with two types of problems fundamentally. When we try to predict the outcome of a dice roll or maybe the mid price, we're dealing with a regression problem. We're trying to predict some sort of quantity, and by predict I mean come up with some sort of expectation or level. And when we're dealing with a classification problem, think something like Face ID, or even trying to predict whether or not the price of a stock is going to go up or down tomorrow, we're dealing with probabilities in the Bernoulli sense, right? We're producing an expectation of a Bernoulli random variable, which is going to give us a probability. And what I have here is a simple example of how you might deploy this in the finance space. So I have a set of returns here, and I have a trading signal, which is going to separate the returns from positive to negative. And If there's a lot of separability because I have a good signal, then it might look like this. This hyperplane creates positive returns on this side, negative returns on this side, so I'll go long here and short here. Well, that's great, but the problem space is very unstable. There's nothing that's going to guarantee that this expectation working out in this case is going to hold moving forward. Now, there are systematic inefficiencies in the market. You can look at options, you can look at earnings, you can look at a variety of trades where on average you will walk away with a profit. You can look at something like even just hedging away directional risk and selling volatility as just a very simple example. But again, when we're dealing with this space, right, you didn't need to deploy AI for that. You just looked at a very fundamental statistic that is the average P&L associated with the trades in that strategy, and you assessed if there was any edge. So when we're looking at trading signals, you can use AI to extract interesting signals in a probabilistic way or even in a regression capacity, but you don't necessarily need to deploy it for the actual return prediction and measuring the signal against the actual returns. You can just use classical statistics for that. Some closing thoughts and future topics. Too long didn't watch. The stock market is fundamentally unstable. If you can't produce an expectation that is valid, then how on earth is throwing artificial intelligence at the problem going to help? If in all of the examples above, we saw it is just learning essentially a nonlinear conditional expectation, sometimes just the expectation. So if you can't produce a good level using classical statistics, how is artificial intelligence going to help? So AI is far from a cure-all, but AI is certainly amazing at certain types of problems. Heavily conditional problems, heavily nonlinear problems, stable problem spaces, time invariant distributions. Very, very useful. Think of things like language modeling. When you talk to Gemini, ChatGPT, you're not concerned it's going to forget English. It's just a model producing expectations too, but it's conditional expectations. Goodness gracious, are they good? Same with your Face ID. AI is not amazing at providing predictions or levels in a random environment, either actually random or where there's insufficient data to provide reasonable levels. Think of something like stock returns. The best that we can do is try to come up with different interesting ways to apply artificial intelligence and machine learning to things that may explain variability in that space. But again, if it's fundamentally random or if it's fundamentally extremely unstable, just throwing AI at the problem, it's not going to help. Some future topics that are interesting: goodness of fit tests for different types of distributions. Is this actually a geometric distribution? Could be very interesting. Are these valid? Can we use these to find an edge in an algorithmic trading capacity? Could be an interesting future topic. Fundamentals of neural networks. Maybe we could discuss how neural networks function, how they learn, back propagation, forward propagation, different architectures. Hopefully there's interest in these topics. Analyzing latent spaces. I talk about stability a lot here. What am I really talking about? Principal component analysis, autoencoders, variational autoencoders, distributional learnings. A lot of very interesting topics in data science I would also like to discuss. And of course, machine learning and artificial intelligence in finance for signal construction and price construction. Let me know your thoughts on these future topics and what you might like to see in another video soon. That's going to do it for this video on what does AI actually learn. I hope you enjoyed. I hope you learned something. If you like this topic and want to see more videos like this one, please subscribe, like, leave a comment below. Let me know. In any case, thank you so much for watching, and I will see you in the next video.